to talk very briefly about the CubeRRT mission. This is an ESTO-funded CubeSat project where we are primarily looking at the development, or actually maturation, of techniques to mitigate radio frequency interference on microwave radiometer remote sensing systems. I'm still not seeing the slide.
The title slide. Go ahead.
So the PI for this project is Joel Johnson at Ohio State, and we are collaborating with JPL, Goddard, and Blue Canyon Technologies. In the interest of time, how much time do I have?
Sorry, roughly 15 minutes.
Okay. Some of the details that were shown for Tempest D are very similar to what we are doing, aside from the instrument. I think the rest of the spacecraft bus and the comms and avionics and all of those things are pretty much the same. And I think Blue Canyon is probably going to address more of the details of that later. Specifically, what we are doing here is a technology demonstration of RFI mitigation techniques, and basically showing that we can use algorithms that are currently performed on the ground with downlinked satellite data, that we can actually put that processor on board a CubeSat and demonstrate that the RFI mitigation algorithms would work in a space environment. Okay.
If you've got the slides in front of you, just call out what page number you're on, and we'll match you here.
Okay. If we could go to the second slide.
Okay.
All right. So I'm not going to go into too much detail about the usefulness of microwave radiometry for Earth observing systems, but suffice it to say, one of the challenges that we face is ever-increasing man-made transmissions that cause radio frequency interference, and this is particularly problematic because we're looking at fairly weak microwave thermal emission coming off of the Earth. And what we're finding is that even operating in protected bands for a system like SMAP, which is the Soil Moisture Active Passive System, we get a fair amount of RFI even operating in protected bands. If we go to the next slide, slide 3.
Okay.
So CubeRRT is being developed to operate over a very wide range of frequencies from 6 to 40 gigahertz, and we are going to operate at 10 specific bands within that range, each with 1 gigahertz of bandwidth. And they roughly correspond to the primary and secondary allocations that are shown on this slide. I'm hoping this is the slide that says spectrum allocations at the top. Basically what we're finding is whether or not we're operating in a protected band or not in a protected band, having a way that we can adapt to the ever-increasing presence of RFI is something that would help numerous radiometer missions into the future. If we go to the next slide, slide 4.
Okay.
Okay, so as I've mentioned, the RFI problem has been recognized for a number of years. It's certainly not getting any better. There have been NASA-funded IIPs and other projects to develop digital backend algorithms for radiometry that can detect and filter out the RFI corrupted data. And some of the members of our CubeRRT team have been deeply involved in those programs. And basically, we're leveraging the algorithms that have previously been developed on these other projects to use them for the CubeRRT mission. Specifically, if we think about the current SMAP system, that's an L-band radiometer, this table on this chart kind of shows the challenge that we're facing, and I think that's relevant to the discussion we're having now, which is have to do with the volume of data that we produce. SMAP currently operates in one band with about a 20 megahertz bandwidth. It's a small enough amount of data that we can downlink to the ground. We can do all of our RFI processing on the ground. But if we think about future systems where we're operating in multiple bands, where we're into the hundreds of megahertz of bandwidth, it becomes much less possible to downlink this higher volume of data to run the RFI processing on the ground, which necessitates developing an RFI processing capability on board the spacecraft, which is basically what the CubeRRT mission is looking to demonstrate. Our intent is to take what we currently consider to be a TRL5 and elevate it to TRL7 for these RFI mitigation techniques. Here's our quad chart. I won't dwell on this other than just to show in the upper right, you can see a picture. Oh, this is slide 6, I guess now. Are we 5? Slide 5.
We got it.
So you see the 6. We're doing a 6U CubeSat just like Tempest D. I think our satellites more or less will look similar, except for we have different antennas sticking out of the bottom than Tempest D uses. But I think most of the rest of the outer appearance is fairly similar. We started a bit later than Tempest D, though. Our project kicked off in January of 2016, and we also have a 2-year development cycle, and we're planning 1 year of on-orbit mission support. Our current goal, or I guess hard deadline, is to get all of our hardware integrated and tested for delivery to NanoRacks in February of 2018. We are also manifest on the Ilana 23 mission, same as Tempest D, so we'll all be going up together. We just had a slightly later start than they did. If we go to the next slide, this slide 6, I guess. This table provides a summary of some of the general characteristics of the operation parameters for the radiometer and the data rates and so forth. As I mentioned previously, our radiometer can operate between 6 and 40 gigahertz. It's tunable. We have 1 gigahertz of instantaneous bandwidth. This mentions emphasis of 9 bands commonly used for microwave radiometry. We've sort of divided up into 10 bands. I'll talk more about the antennas later, but we're looking at circularly polarized radiation, 400-kilometer altitude. The spatial resolution that we're looking at is not quite as good as what Tempest D has, but that's okay because, again, we're here to more demonstrate the back-end processing than getting high-resolution radiometry results. Let's see. So looking down, we have capabilities to do both internal and external calibration, cold sky calibration, as well as reference loads and noise diodes on board the spacecraft. And jumping down to the last 2 cells of this table, we're expecting an average payload data rate of about a little over 9 kilobits per second. That's assuming a 25% duty cycle of the operation of the system. This amounts to about 100 megabytes per day. And looking at our direct downlink capability using the cadet radio, we're expecting that we could get 135 megabytes downlinked with 1 daily contact, which should be enough, assuming that we can get at least one daily contact. So that kind of shows you the data rates that we're having to deal with. As is the case with Tempest D, we have Globalstar as a backup system. And again, Blue Canyon will talk more about how that would be used. But primarily, we're looking at using direct downlink with the UHF cadet radio. Next slide would be slide 7. As far as how the team is dividing up the work, we are developing the payload into 3 primary subsystems. We have a radiometer front end, that's being developed at NASA Goddard, and the digital backend, the processor that does the RFI detection and mitigation, is being developed at JPL. And the microwave antennas are being developed here at Ohio State, with Ohio State also having the lead on the project and the overall system integration authority. We have contracted with Blue Canyon Technologies to build the spacecraft bus and to do the full system integration and testing at their facility, and then delivery to NanoRacks, again for launch in 2018 on Alana 23. Next slide. So I've got a few slides that I will gloss through fairly quickly that show some of the details of the hardware that are currently being developed. At this point, we are building the flight model subsystems for the radiometer front end and the digital back end. The radiometer front end again is being built at Goddard, and two primary components. We have a microwave assembly that connects directly to the antennas that brings in the radiation, and then we have an LOIF and a control board assembly that connects there. So it's a heterodyne receiver. We then send that the signal that comes off of that to the digital back end. Next slide. I think we're focusing in on the fact that we had to make some late modifications on the microwave assembly, switching to some coaxial low noise amplifiers that we previously were having some difficulties in our engineering model, but we think we have that all figured out now. Next slide should be slide 10, and that shows some drawings of the microwave assembly, the low noise amplifier, and in the upper right, how that fits into the payload section of the spacecraft bus. Let's go on to the next slide. Here are some pictures of the local oscillator intermediate frequency, or the LOIF boards. These are fairly standard electronics that are being developed at Goddard, and again are in the process of flight model builds as we speak. Next slide shows the engineering model of the various components of the radiometer front end being tested at Goddard. This is just really to show you that we actually did build some hardware, and we've actively tested. Our engineering model tests have all been completed, and we are full steam ahead on flight model development. Next slide should be slide 13. This talks a bit about the radiometer digital backend processor. Again, this is the part that's being developed at JPL. And here we are bringing in signal from the radiometer front end and performing the RFI detection and mitigation algorithms on a zinc FPGA. And we've built-in cross-frequency and kurtosis algorithms allow us to deal with narrow-banded signals and pulsed signals alike. So we've developed the algorithms to deal with multiple types of RFI that we might encounter in a typical mission. And we've built numerous engineering test units that we kind of went through a learning curve on the implementation of these FPGAs, running into some issues with how we can upload the code through Flash. There were some problems with the first two, so we built a third that addressed that, and then we built a fourth using a smaller chip that would help us to reduce power consumption. And through all of that work, we've got a design that has us well under our power budget, and the flight model boards are being built as we speak. Next slide shows some of the engineering test units being tested at JPL, and so far everything seems to be working just fine. We are doing a lot more in, we had originally, a lot of our plans had a lot of the algorithms being implemented in firmware. We're finding that that for power consumption purposes, it was actually better for us to deal with, to implement them in the software rather than the firmware. So that was sort of a change that we made as from engineering model through to flight model. Next slide should be slide 15, and this is a picture of the antenna system that we've been developing at Ohio State. And the challenge here was to be able to cover 6 to 40 gigahertz with a reasonable gain. And my colleague Chi-Chi Chen has came up with a series of 3 helical, or they're actually tapered helical antennas that are mounted inside of an Ultem radome that has this intricate pattern cut into it so that we can try to enhance gain as much as possible while maintaining physical stability, so that when this radome gets deployed from the bottom of the spacecraft, the antennas stay relatively stable. Let's see. I think if we go to the next slide, slide 16, just a little bit more detail on how the antenna assemblies are put into place. The following slide, slide 17, shows overall system performance. At least this is simulated, and so you can see in the middle column the gains from the low frequency antenna up through to the high frequency antenna. We're meeting the requirements that I had showed on one of the earlier slides. The next slide discusses the CubeRRT spacecraft. Again, Blue Canyon is going to talk about that. If we could go to the subsequent slide, slide 19. This basically shows what the 6U satellite will look like in its stowed configuration, with the solar panels folded down along the sides and the antenna radome folded up underneath on the bottom of the spacecraft. After deployment, when it's in operation, it looks like the picture on the right, where the solar panels are deployed in a canted configuration. I believe it's exactly the same as what was shown for TIPUS-D. And the antennas, that antenna radome swings down from the bottom of the spacecraft into a deployed configuration, and it's a nadir-looking configuration. We then can yaw steer the spacecraft to get us better exposure to the sun. We can also do an operation where we can point the antennas at cold space for calibration purposes. The next slide, very briefly talking about our operations when in orbit. I said on a previous slide that we were assuming 25% duty cycle. It's possible we could get as high as 33% duty cycle, but that depends on battery depth of discharge and a lot of other factors. We're going to emphasize, because working with a 25 to 30% duty cycle, we're going to emphasize land observations, which is where we see most of our RFI. So our plan is to turn the instrument off when we're over ocean, turn it on when we're over land. And we've had some thoughts about the South Atlantic anomaly and understanding what it did to the SMAP active system. So as a risk mitigation, we're planning to turn the payload off when we're over the South Atlantic anomaly. That may be overkill, but that's our plan for the moment. And we've got a table-driven tuning of the various frequencies so that we can operate in multiple modes, where we can step through all of the frequencies in all measurements, or we can sit at one frequency and just take measurements in an orbit all at the same frequency. We have a great deal of flexibility in how we operate the instrument. And we're currently working on an ICD between Blue Canyon and OSU to develop the process by which we will provide the commands and to look at the telemetry and science data that come off of the system. The next slide just shows kind of an overview of where we're anticipating 1 year of operation. That might be a bit optimistic, but that's our hope. And assuming operation of 30 minutes per orbit, and frequency switching every 10 seconds. We feel that we should be able to meet our baseline mission objectives, which is 10 hours of operation in all 10 frequency bands. We should be able to do that in the first couple of weeks. I guess our intent is to get significantly better than that, obviously, and as much land coverage as we can possibly get over that 1 year. But we think we can get probably 99% land coverage at each frequency, and that goes toward meeting our sort of extended mission requirements. That's the next slide, just our conclusions. So we're basically validating the RFI detection and mitigation technology that would assist in future Earth-observing microwave radiometry systems. And basically our payload flight model is being developed currently. We're looking at integration with the spacecraft at the end of September, early October, and that should put us right in line for delivery of the system to NanoRacks in February of 2018. Any questions?
Chris?
This is Brian Albert from Wallupset. I had a question just regarding the comm link, if you could comment on that. Yeah, I believe you said you're using the Cadet and the Wallops ground station, and you're looking to get 135 megabytes per pass. I don't know if you'd had there's been any experience with that, actually downlinking that much data during a single pass.
I don't know. I would defer that question perhaps to Blue Canyon. They're currently working with Wallops to figure out some of these details. Matt, are you on the line? Do you have any response to that question?
In terms of actual experience of getting that much data down, I don't know heard anything. We did some analysis to show, kind of minimum contact times from an ISS-like orbit over a year, and what that comes down to when you, get your 3 megabits.
Right. So I guess it's just a cautionary note then. I don't know that anybody has done that before. Just a little bit of background on that. The Cadet's got frame sync in the very beginning of the transmission.
Yep.
And nothing throughout the actual transmission. So there's concerns of if you do a link or a data dump that is too long in duration, you increase your risk of losing sync with your data. So we for IceCube,